Today's lesson is the graph of what your book refers to as reciprocal functions. You may also, in the future, you may see these referred to as inverse variation functions. So let's just take a look at the type of function that we're talking about. We're going to start with a parent, and then as usual, we're going to do the transformation of this particular parent. So we're just adding to the family of functions that we call the parent functions, those functions that we've previously looked at in other lessons. So let's just go ahead and I'm going to do the graph, and then we will be able to fill in some blanks. I think the blanks will make a little bit more sense once we have the graph to look at. So I'm going to make a table of values, just a little XY table. And obviously we have a number that's an input that cannot be allowed. We have an input that's not allowed. What is that? We cannot let x be 0. Okay? Pretty obvious. You can't divide by 0. It's also true that there is no possible way to input something and cause y, or f of x, to become 0. Okay? So far, what we know about this graph is we cannot let x be 0, no 0 as an input, and the function will never be 0. It's impossible to input something for x and make the function become 0. So for that reason, we have two asymptotes. So I want you to draw this dotted line to represent a vertical asymptote, because since the function can never equal 0, that's like saying y can't be 0, and we're going to identify the y-axis and the x-axis as, you can kind of think of this as they're off limits. Our graph cannot touch either one of those, where x is 0, which is the y-axis, nor where y is 0, which is the x-axis. So this particular graph, as we talk about characteristics, it has a vertical and a horizontal asymptote. Okay, so let's plug in some actual numbers that can be inputs, like 1. If I input 1, f of 1 is 1. If I input 2, f of 2 is 1/2. If I input 1/2, 1 divided by 1/2 is the same thing as 1 times 2, which is 2. Okay, so I'm going to go ahead and plot those 3 points. Just like normal, we go to our origin and we plot the point 1, 1. We plot the point 2, 1/2. And I'm going to plot the point 1/2, 2. Now again, I'm going to follow these two asymptote lines as I draw this curve through these 3 points. So I'm never going to touch, I'm going to approach but never touch the y, and I'm going to approach but never touch the x. Well, the thing about reciprocal functions is that they are always in two parts. We technically call these parts branches. So if you were to stop here with the graph, you would be half right. So just keep this in mind. If you choose whatever 3 numbers you choose for positives, make sure you choose the opposites of those. So it would be okay if you wanted to show the table like this, because now I'm going to input -1, and that gives me an output of -1. I'm going to input also -2, and that gives me an output of -1/2. And if I input -1/2, I'm going to get an output of -2. And now this is the complete graph. So make sure you're careful when you draw this reciprocal function that you include both branches. So that leads us to this blank I have. What type of graph is this? Well, I don't know if you've talked about this in previous math classes, but This is really, you can think of it as two parabolas that open opposite each other, and the technical word for that is a hyperbola. I'm going to erase my table so I can have a little bit of room. So the type of graph will always be a hyperbola, so hopefully that'll help you remember to include both branches. I went ahead and wrote the domain and range. This is kind of wordy. We could be a little more concise here, and we could just say that for both the domain and range of the parent, x can't be 0 and y can't be 0. That's basically what this is saying. We travel from negative infinity to 0, but remember in interval notation this means that 0 is not included. Remember the parentheses? If it had a bracket there, it would mean that 0 is included. So it's like saying all of this up to 0, and then you jump over 0 and you include all this, and that happens also for the range. You travel from negative infinity up to 0, can't count 0, it's not part of the range, we'll jump over 0, and then we'll pick up the rest going to positive infinity. So once again, we have two asymptotes where x is 0, that vertical line, which is another way of saying the y-axis, and f of x is 0, that horizontal line, which is another way of saying the x-axis. There are no intercepts for the parent, and again, we do not have a definition. This function is not defined if x is 0 because you can't divide by 0. So now that we've got some of the characteristics out of the way for the parent, let's take a look at the transformation of the parent. This is a review, just like we've done in the past. Shifting the parent left, right, up, or down. Making the parent be a little bit larger, or in this case further away from the origin. So here's the way I want you to handle the transformations. Here it is in general, and we're going to do this specific graph. So just like we've done in the past, I want you to think about a table of values just for the parent. And if we lifted the parent out of all of this, we would have f of x equals 2 over x. So let's start there with a table just for the parent. Again, you cannot input 0, but we can input 1, output 2, we can input 2, output 1, 2 divided by 2 is 1. And basically, I try to choose numbers. The inputs really depend on what this numerator is. To me, it makes sense to do 4 because that's pretty easy to plot, 1/2. If you input 3, that's okay. You just have to estimate 2/3. And then don't forget, we're going to need to do the opposites of these. So I'm okay. Some people don't like to do this. I'm okay if you show your table like this. Positive negative 1 gives you positive negative 2. Negative 1 gives you negative 2. So if you want to just indicate these with plus minus, that would be fine. Save you a little bit of writing. Okay, well we got the table for the parent. Now let's take a look at how this parent is being translated. Looking in the denominator first, we're already used to this kind of thing with previous parents. Can somebody tell me what kind of movement is indicated by this plus 3 in the denominator? Which way are we going and how many? Anybody want it? Nobody wants it? Yeah. Left 3. Everybody see that? Whenever we're adding or subtracting to x, it's always a horizontal move, and it's tricky because it's really the opposite. So since I'm moving left 3, I no longer have a vertical asymptote of the y-axis like the parent typically does. It now has a vertical asymptote of x equals negative 3. So I want you to draw dotted lines to represent the asymptote lines on these graphs. So in essence, we're showing that this entire parent graph has been moved 3 places to the left. This outside number indicates vertical movement, and in particular, what's it telling us? Where are we going? Down 4. So instead of having a horizontal asymptote, which is the x-axis, that's what the parent would have, this translated parent is going to have a horizontal asymptote of y equals negative 4. So these numbers, if they exist, the number plus minus in the denominator will tell you where to put your vertical asymptote. And it's tricky, so be careful. Plus really means to the left, because it's really h is negative 3. Outside will tell you where to put your horizontal asymptote, and it's not tricky. Negative means down, plus means up. Okay, so here's how we're going to graph this translated parent. I'm going to go back to this table that we created a couple of minutes ago, and we're going to plot these points, but we're not going to plot them from here. We would if we were just graphing the parent. Our origin has been shifted. It's now here. So we're going to treat the plotting of these points as though they're being plotted from this new origin. Okay? So I'm going to plot just like this. I'm going to plot the point 1, 2, but again, treating this as the origin. Right 1, up 2. Now I'm going to go right 2, up 1 from this new 0, 0. I'm going to right 4, up a half. And using my vertical and horizontal asymptotes as guides, I'll just draw a curve through those points. So that's one branch, and then I do the same thing for the negatives. Again, this is your new origin where those two lines cross. Don't plot from here. You're going to plot from here, and we'll do negative 1, negative 2, negative 2, negative 1, negative 4, negative a half, and we have the other branch. And there's the graph. Any questions? Everybody good? I guess a common mistake I see is people starting here and then they try to input numbers back into this. Do not input into this. I'm telling you, it's much, much easier just to input into the parent, and your shift has already been taken care of by drawing these new asymptote lines. So treat the intersection of those two lines as your new origin from which to plot these parent points. Okay, so let me help you with some specific homework problems, and then you'll be ready to practice. For problems 7 through 10, you're going to be provided with a graph. You're also going to be provided with the function represented by the graph. Your job is just to identify these parts. Okay, so I just took a picture of a graph like what you're going to have on 7 through 10. So let's start with the asymptotes. I could spell. To me, it's easier just to look at the function that's given. I mean, the graph is great, but if you look at the function, you can tell what the horizontal asymptote is. You just look at the denominator. This indicates a shift of where, or what direction in the denominator. Say it again. Right 1. Okay? So the parent always has a vertical asymptote on the y-axis, but if we move right 1, we now have a vertical asymptote at x equals, I'm sorry, I wrote horizontal asymptote. Let's change this to vertical. Sorry about that. Since we moved right 1, we now have a vertical asymptote at x equals 1. Now let's take a look at the horizontal asymptote, and you can always know what that is by anything that's added or subtracted outside or to the right of the fraction. Just go back here, just like this number k will tell you what the horizontal asymptote is. Well, there is nothing. If you look in the square where the function is written, there is no number being added or subtracted to the function, so the horizontal asymptote is still the x-axis. Or in equation form, we would say y equals 0. The reason why looking at the graph might be a little misleading is because these are not in units of 1. So it's kind of hard to tell, okay, well, what exactly is that? But you can tell exactly by looking at the function. That's a horizontal asymptote, y equals 0, and vertical of x equals 1. All right, we also need to state the domain. Well, the domain, we're going to make it simple. Instead of doing interval notation, I'll save you a little bit of time. It's essentially every x except for 1, the number 1. And you can grab that, you can know what that domain is just by looking at the vertical asymptote. So I'm going to write it as all x such that x can't be 1. We know that because we have a vertical asymptote representing basically where the graph is off limits. It cannot cross through x equals 1. The range. Well, the range really hasn't changed from the parent. The range we can get from the horizontal asymptote, so we'll say f of x such that f of x can't be 0. So the short answer to this is, if you want to know how to state the domain, look at the vertical asymptote. If you want to know how to state the range, look at the horizontal asymptote. And you cannot let either x nor y be that particular number. All right, we're done with letter A. Let's try letter B. We'll start with a vertical asymptote. Vertical lines always start with x equals. So Casey, can you tell us what the vertical asymptote would be in this case? X equals -2. Very good. There's also a horizontal asymptote. There'll always be one of each. And Maggie, can you tell us what that is? Y equals 1. Very good. State the domain and range. We'll start with the domain. So Devin, it will be all x such that -2. Okay, can't let x be -2. And Sarah, what about the range? Okay, f of x such that we cannot let f of x be 1. It can be anything besides 1. All right, do you have any questions on problems like 7 through 10? Look at the graph, state the particulars. Okay, let's do a couple of graphs, and then I'm going to turn you loose on this assignment. Once again, we did a problem sort of like this at the beginning. Start with a table for the parent. The parent in this case is just 3 over x. So our table of values, if x is 1, f of x is 3. If x is 3, f of x is 1. You can do anything you want. I like to pick numbers that make it easy to graph, like 6. If x is 6, f of x is 1/2. And then don't forget, you need the opposites of these as well. So you can just think of these as plus minus, plus minus. Now, before you start plotting these, you need to go ahead. We have a shift. The parent has been moved, according to this, 2 places to the right and 4 places up. So the way I show that movement of 2 places to the right, I move the original vertical asymptote, which used to be the y-axis, but now it's going to be the line x equals 2. That's going to take care of the 2 places right. And the way I take care of the 4 places up is I take this original horizontal asymptote, which is the x-axis, and I just move it up 4 places. And I draw another dotted line to represent my new horizontal asymptote. So where these 2 asymptote lines cross is the new origin. It is from this dot that you're going to plot these 6 ordered pairs, the 3 positives and the 3 negatives. So let's see, 1, 3, 3, 1, 6, 1 half. There's a branch. And now we'll do the negatives. Negative 1, negative 3, negative 3, negative 1, negative 6, negative a half. And there's the other branch. And now we just state the domain and range and we'll be done. So let me see, maybe Hannah, can you help us out with the domain? All x such that x can't be 2. And Kate, what about the range? Four. Good. Now we're done. Any questions? Not bad, is it? Pretty easy? Okay. Thought I would try one more. What do you notice that's different about this one? Got a negative. Let's see what the effect of the numerator being negative has on the graph. You probably have already guessed. We're going to do a table for the parent. Here's the parent, just lifted it out. So once again, I'll do those usual inputs, or at least inputs that make it easy to calculate, like 1, negative 6. If I do negative 1, I'm going to get a positive 6, right? We'll just keep on working our way down. We'll do the positives first. If I input 2, I get negative 3, and I can do 6, negative 1. Okay, now I'm going to come back and we'll plot both these and their opposites in just a minute. Let's take care of the asymptote lines because this is a shift in 2 different places. So let's see, Zach, this denominator indicates a shift of which direction?
Left 4, left 3.
Left 3, good. Okay, so let's draw a vertical asymptote through x equals negative 3. That takes care of the left 3 shift. And Whitney, this negative 2 tells us what kind of shift? Down 2. All right, so we'll indicate that with a horizontal asymptote. Now something interesting is going to happen when the numerator is negative. Let's start plotting our points. Remember, where these 2 asymptote lines cross, that's the new origin. This is where we're going to start plotting. So here's 1, negative 6. Right 1, down 6. 2, negative 3. 6, negative 1. And there's a branch. You really just need 3 points for each branch. I'll try it from this side. Okay, now do the opposites. If you do negative 1, you should get positive 6. Negative 2, positive 3. Negative 6, positive 1. And there's the other branch. So you can see that the negative numerator just flips the branches. Instead of starting off in quadrants 1 and 3, now they're 2 and 4. And that should always be true when the numerator is negative. All right, any questions? you're ready to start, and it's just those graphs for tomorrow, and I'll let you work on those, and just let me know if you have any questions.